Okay, so 7.4 is our introduction into matrices. So we're going to do a bunch of stuff eventually with matrices, add, subtract, multiply. That's in the next couple of sections. But for today, we're going to learn how to solve a system. Well, we're going to learn about matrices first, like just the foundation of it. Thank you. And then we're going to learn how to solve a system using matrices. So first, what is a matrix? Okay. It is a rectangular array of numbers with m number of rows and n number of columns. And you will be asked an easy question, which is what's the order of the matrix and or the dimensions, because those are the same thing. What are the dimensions of the matrix? And this is the number of rows by the number of columns. And you'll keep it just like that, like it was a 2x4, like you would write it like that. So rows go horizontal. This would be a row. This would be a row. This would be a row. Columns go vertical, just like if you could picture columns on a building, right? They're vertical. Columns go vertical. So if it had asked for the order of this matrix or the dimensions of this matrix, this is a 3x2. Today we're going to focus on, in a little bit, we're going to do 3x2s, which is meaning that you have 2x3s, which means that you have two variables and two equations. And then we're eventually going to get into ones that have three variables and three equations, and we're going to learn how to solve it. All right, example 1 just says find the dimensions. Again, this would be the same thing as finding the order. So what's the dimension of A? 2x4. And what is the dimensions of B? 3x1. Then we get to something called an augmented matrix. So a matrix is formed by literally writing out just the coefficients and the constants from a systems of equation. When you write these, the sign goes with them. So when I am taking negative 2x plus 3y equals 7 and rewriting it in a row, it would be negative 2, positive 3, positive 7. And then 5, negative 4, negative 10 would be 5, negative 4, negative 10, just like that. You will see it written like that, and sometimes you will see it with two little dots where the equal sign was. Eventually, we will eliminate those two dots, but you can see it both ways. I would say either way is right if you're just writing the matrix from the equations. So the x's go, the y's go, the constants go. If it was an x, y, z, if it was three variables, it would be x, then y, then z, then the constants. And weirdly enough, if there's four variables, w gets put at the end. It'd be x, then y, then z, then w, and then the constants. We will not be solving things with four variables, but you might be asked just to write the matrix from it, or vice versa. Good so far. All right, example 2 says write the matrix from the system or the system from the equation, or the system from the matrix. So for A, what's my first row? 7, 4, negative 1, 10. What's my second row? 1, negative 5, 0. Good, there's nothing there and you need the placeholder. 17. And then you put little brackets on this to say that that is a matrix. So not parentheses, not solid one line, but an actual bracket.
Could we get more than 2 equations?
Sure. Yep. All right, B now goes in the reverse order. So here's the matrix. Remember, it is variable, variable, variable. Last one is constant. So it would be x, y, constant, x, y, z, constant, x, y, z, w, constant if there was 5. So I get negative 7x plus 2y plus z equals 4. And I get 5x minus 3y. You can put plus 0z, but you also don't need it if you want to skip it, equals 15. So you can rewrite, I would take both those answers, with the 0z or without. Still good? Yes? Okay, now here's all these operations we can perform on a row in a matrix. We can switch two rows. So we could literally take row 1 and row 2 and switch their locations. We can God bless you. We can multiply a row by a non-zero constant. So let's just say it said 1, 2, negative 3, 4. I can do row 1 times 2, which would multiply 2 times this whole row. And I'd get 2, 4, negative 6, 8. So that's one of the operations we can do. We can either switch them, we can multiply, or we can add two rows or add a multiple of a row to another row. So let's say I had 1, 2, negative 3, 4, and then 1, 2, 3, 4. I can add these together. I'd get 2, 4, 0, 8. So everything basically you could do when we were doing elimination on our systems of equations, we are going to do to these matrices. The difference is you won't have a variable there. So we're going to manipulate these. So there are zeros in the place of variables, which would mean we canceled out the variable. And then we're going to solve what's left, just like we did with elimination. Now notice it said multiply here. You could also multiply by a fraction, which is technically dividing. So if I had 2, 4, 6, 8, and I wanted, let's say I wanted that first term to be a 1, I can multiply everything by a half. So instead of dividing by something, we say we multiply by the reciprocal or we multiply by that fraction. It does the same thing. All right, so example 3 says identify the elementary row operation or operations, plural, being performed to obtain the new row equivalent matrix. So it's saying this is my original and this is my new one, and I want to know how I got from one to the other. So go through your checkoff list of things you can do. Were the rows switched? No. Was one row added to the other row? No, sorry, let's start with multiplication. Can I multiply? So what did change was row 2, right? Row 1 stayed the same, but look at row 2. Can I multiply row 2 by something from the original to get to the new one? No, there's nothing I can multiply 3 by to get to 14. That would be the same as negative 1 to get to 0 or 2 to get to 13. That leaves the third option, which is either add them. If I added as they were, it would have been 5, 3, 7. That's not it. Or add a multiple of something. So did something change by multiplying by something and then add to the other one to get my new row? Can you see it? Stare at it for a little bit.
Is it 4?
What's 4?
Like multiply by 4?
Multiply what by 4?
Oh, the second.
So multiply, let's try it. Multiply the second one by 4 and then add it, you're saying, right? Yes. So if we multiply by 4, we do 4R2. I get 12, negative 4, 8, and I add it to row 1, 2, 4, 5. Do I get my new row? Yes. So the way we would show that notation is, good job, Camilla, 4R2. So we multiplied R2 by 4, and then we added it to R1. Order there doesn't matter. I could have done R1 plus 4R2. Now, some people's brains just like see that, and that's great. And then the rest of us are like, huh? For me, I would have like tried with the negative 1. How do I get from negative 1 to 0? By adding these two, I would have had to change this negative 1 to a positive 4. And by doing that, I'd have to multiply everything by 4 and then see if it works, and that's what worked. Questions so far? You can either switch them, multiply them, add them, or multiply and add. All right, example 4 says fill in the blank using the elementary row operation to form a new row equivalent matrix. So this is my original, this is my updated one. Step 1 would be try to figure out what change is there and then actually do it to the one that's missing. So row 1 did not change, right? How did row 2 change? You divided by 5, but we can't divide by, which means we multiply by a fifth. So it's 1/5 times row 2. That's the notation we would use. So it's already done to the 5. It's already done to the 7. I have to do it to the -10. And what should be in that empty space? -2. Everybody good?
Do we have to write that nothing changed in R1?
No, you just say what did change. Yep. All right, this is called row echelon form. We're going to get to 2 goals here, like 2 checkpoints almost, and that's going to be one of the major steps into solving a systems of equation. And the first is putting our matrix into row echelon form. Row echelon form has the following properties. The rows consisting entirely of zeros occur at the bottom. So if there is a full row of 0, it has to be in row 3 or row 2, the bottom row. And then for each row that does not consist entirely of zeros, the first non-zero entry is 1. And what that means in like normal words is that if I look from left to right in my matrix, the first number other than 0 has to be a 1. So if I look at the 2 by 3, this first number is a 1. This one's a 0, which is fine. The next one needs to be a 1. So that would be in row echelon form. And then there will be numbers in all these places. So this could be like 1, 2, 3, 0, 1, 2. That would be row echelon form. The other way to spot it is there is a diagonal of 1s and a 0 underneath it. All the rest can be numbers other than 1s and 0s. But there has to be a diagonal of 1 with a 0 beneath it.
Like in the second row start with 1?
No, it has, well, it's if you have to have a 0 there. There has to be a non-zero number in the second spot. Yep. So you're looking diagonal of 1s, 0s to the left or like underneath it.
Why is the last one red and it is not?
The little name, this thing.
No.
Oh, I just made up numbers. Yeah, I just put numbers in. Those numbers can be anything. Yeah. So if you look at now a 4 by 3, so a 3 variable one, your diagonal of 1s is here. Anything under it has to be a 0 in order for this to work. So if I go row by row, the first non-zero number is a 1. And then that last thing, number 3, says for 2 successive rows, which is why, Kevin, this is why that answer couldn't work. The leading 1 in the higher row is further left than the leading 1 in the lower row. So it has to be a diagonal that goes top left to bottom right, okay? And then all of this would be other numbers. So a row echelon form for 3 variables would be 1, and then any numbers, 2, 3, 4, 0, 1, 2, 3, 0, 0, 1, 2, something like that. You have a diagonal of 1s, and you have 0s underneath that diagonal. The rest of the numbers can be anything. This is called row echelon form.
Can the numbers that like can change, can they be negative or they?
Sure, they could be negatives, they could be zeros, they could be fractions, they could be whatever.
Okay.
Yep, they just can't, the 1s have to be the 1s and the 0s have to be the 0s.
Okay.
Yep. That's row echelon form. Now, reduced row echelon form takes it a step further. Reduced row echelon says there has to be a diagonal of 1s and 0s above and below it. The only non-1 and 0 numbers would be the last row or the last column, which is your constants. So in these, diagonal of 1s, 0s above and below, diagonal of 1s, 0s above and below. The only non-1 or 0 numbers are the last column, which is actually your constants. So we're baby stepping our way into using these to solve systems. But know the difference between row echelon form and reduced row echelon form. Reduced is the 0s above and below. All right, so example 5 says determine whether the matrix is in row echelon form. If it is, determine if it's in reduced row echelon form. So do I have a diagonal of 1s? Almost. The bottom is what? 0, but what was the rule on the all 0 row? It has to be at the bottom, so that's fine. It is at the bottom. So now look at the rest of that diagonal. Do you have a diagonal of 1s? Yes. Are there zeros below it? Yes, that means row echelon. Are there zeros also above it? Almost. What's wrong? This 1, 1 means it is not in reduced row echelon. So it is in row echelon, not in reduced row echelon. That's RREF is actually how your calculator puts it. Reduced row echelon form. Yeah. Because that 1 has to be a 0. There has to be zeros below and above for reduced. This 1 messes that whole thing up.
I realized there has to be zeros next to it.
Yep. Yep, no, but above the diagonal, meaning all the space above and all the space below has to be zeros. The only non-zero and 1s could be that last column. All right, here is the whole purpose of learning how to do this. And that is solving a system with something called Gaussian elimination and back substitution. So there's going to be 2 methods we're going to learn. Gaussian elimination with back substitution and Gauss-Jordan. Gaussian elimination with back substitution means you're going to rewrite your matrix. So you're going to take your system, you're going to write it in matrix form. Then you're going to use all the different elementary row operations, either multiplying, adding, moving, to put your augmented matrix in row echelon form, which means your diagonal of 1s, zeros below. These are all other numbers, right? We're going to put it in row echelon form. And if you've done that, then you're going to write a systems of linear equations that will have 1 variable at the bottom, 2 variables in the middle, 3 variables at the top, which is your triangle system. And then we're going to use back substitution to solve it. So let's say we go through all the work, which we're going to do a bunch. That's going to be the big part. But we're going to work through all of these steps. And we're going to, at the end, have something that says 1, 2, 3, 4, 0, 1, negative 2, 3, 0, 0, 1, negative 1. Why is it not showing? Let's say after we did the work to get it into row echelon form, my system looks like this. Rewrite that in equation form. So what's my first line? X plus 2y plus 3z equals 4. Remember, the last one's always the constant. Next line. Y minus 2z equals 3. Next line. Z equals negative 1. There's your triangle system. And you use back substitution to solve it. So z is negative 1. I take the z, I plug it in. I get the y. I take the z and the y, I plug it in. I get the x. And we're going to solve the system this way.
Didn't the last row have to be all zeros or no?
No, only if there is a row of all zeros, it has to be at the bottom. But typically there is not a row of all zeros.
Okay.
It's just that by rule it has to be at the bottom.
Okay, but it has to be under the 1s.
Correct.
So it couldn't be 0, 1. It has to be 0, 0.
Correct.
I mean, negative.
Yep.
Okay.
All right, I'm telling you right now, it's going to be weird in the beginning, people, but we're going to make it through. This is one of those things that if you practice this over and over again, I promise you will get good at it. But if you are watching an episode right now and you haven't moved your finger or your stylus, maybe you want to make a different life choice moving forward. All right, so we're going to start. All right, ready? We're going to write it in a matrix form. What's my first row? 1, 2, 7, second row. 2, 1, 8. Do I have a diagonal of 1s?
Yes.
Yes. Do I have zeros below it? No. Okay. So here's what I have to do. And this is, I would recommend this order, but there are times in which these get weird and you cannot do it, and it makes more sense to do it a different way. It doesn't mean you have to do it this way all the time. So for me, the first goal I always do is to get a 1 in the top left spot. I start there because it makes the rest easy. So because that 1 is already there, I don't need to do that. But let's just say these rows were switched. Let's say this started as 2x plus y equals 8, x plus 2y equals 7. And I rewrote it as 2, 1, 8, 1, 2, 7. The very first thing I would do is switch those rows so that the 1 is in that top left spot. Yep, you can switch any row you want, as many times as you want. Omar, you getting all this? All right, now that that is already there, my second step is to get a 0 below it. So I want a 0 here. I cannot multiply by 0, right? That was a rule. You cannot. You can multiply by a non-zero number. I can't. Otherwise, I eliminate the whole row. I can subtract. Huh? I can't subtract. I can add, or I can multiply. If I add these rows, does that 2 become a 0? So think about how we solve systems. How do I eliminate a variable? I would multiply the other row by what? -2, and then add these. Yep. So I'm going to multiply. I'm going to write out every step. I'm going to multiply row 1 by a -2, and then I'm going to add it to row 2. So we're going to write that notation because if you want any ounce of partial credit, you got to give me the play-by-play. Yeah. So I'm going to do this. And also when you find your own mistake, it's going to be easier to backtrack your steps by knowing what you did. So -2. So I'm temporarily changing row 2. Only to use it to replace, row 1, sorry. Only to replace row 2, but initially I'm going back to my regular row 1. What do you mean? Oh, I just said if it had started that way, my very first step would have been to switch rows, but it did not start that way, so I'll erase it so we don't get confused. Okay, so -2 times row 1 is -2, -4, -14, and I'm going to add it to row 2, 2, 1, 8. And I get 0, -3, -6. Now listen carefully. When I add row 1 and row 2, I can replace either row 1 or row 2 with my new row. Not both. So which row was I trying to replace? Row 2. So I'm going to leave row 1 alone. I'm always going to write my original in pink so that I know that it's like when I go back to my thing. I'm going to leave row 1 alone, and I'm replacing row 2 with 0, -3, -6. The 1 is gone, which is why I never try to get the diagonal before I get the zeros. You want to go 1, 0. Now I want to go 1. Now I want a 1 here. What can I do? It could be negative, but it needs, well, then I'd have to change it positive. But I want this, I want to get this without losing this. I can multiply by its reciprocal. So even go further and make it a -1/3. Good. So I'm going to do -1/3 times row 2. And I get 1, 2, 7, 0, 1, 2. So that last step, once you get the 0 in the row, you're always going to multiply by the reciprocal. It's the easy, if you want the 1 there. Okay, so now is this in row echelon? Yes, I have my diagonal of 1s. I have my 0 below. So from here, I'm going to put this into equation form, which would be, what's my first row? X plus 2y equals 7. What's my bottom row? Y equals 2. I already know y. Then I'm going to take the 2 and I'm going to plug it in. X plus 2 times 2 equals 7. And x equals 3. Oh, that's a 3. You can barely see it. So we went 1 in the top left spot. Second, get the 0 below. 3, get the 1 next to the 0.
On the test, can we just, you just have to solve?
You're not going to do a 2 variable on your test, probably.
No, could we just convert it to a system and solve it?
Mm-mm.
We just have to solve it.
Mm-mm. I know. I know.
So you're gonna make us do it this way?
Mm-hmm.
How why not?
Mm-hmm. Oh, just wait. There's 3 variables. We haven't even gotten there. So much fun. So much fun. Yeah. So there are going to be questions in which you get to choose, and then there are going to be questions that says use Gaussian elimination with back substitution, and you have to use this method. You're welcome. No. All right.
Does this translate to real life?
Uh-huh. It's solving a system.
No, like,
What happens if you're in the grocery store and you're like, I need apples and oranges. I have $15. Each orange costs 25 cents. Each apple costs $1.25. How do I spend, how many apples and oranges can I get?
Why I spent
matrices to...
Let's be honest. Most of what you're learning in high school is not actually applied to real life. Your job right now is just to be a student and power through. Okay? You're learning how to learn right now. All right. Ready? So fun. This is taking over your new 1, new 2. So instead of doing that process, you will do this process. I know, it's so much more fun, right? We're going to number these. 1, 2, 3. Take a deep breath, people. You know what really does not help your scenario? Whining about it. Yeah. All right, I'm going to rewrite my matrix. My first row would be what, Javi? What's my first row? I know you don't know. That's why I called on you, friend. 3, -2, 1, 15, -1, 1, 2, -10, 1, -1, -4, 14. Now you miss a negative on that step. You just messed up the whole rest of the process. Write it slowly and carefully. All right, so what was my first goal?
To top left.
Top left. What could I do?
You could switch the top.
I can switch row 1 and row 3. If there's a 1 somewhere in that first spot in one of those rows, switch it. So I'm switching row 1 and row 3, and the little notation for that is like a sideways arrow, just like that. Mm-hmm. So I get, huh?
You can't just tell, like, so we write it out.
You're going to write it out. Trust me, you're going to make a mistake along the way, and you'll want to know what you did. Okay, what was my second goal? The 0 below that 1. So I want a 0 where the -1 is. How could I get it? Now I can add row 1 and row 2. I can add row 2 and row 3. I can multiply one of them and add them together. I can add row 1 and row 2.
Then wouldn't the top would disappear?
No. You can replace either row 1 or row 2 with it, so we're going to replace row 2. And listen, like when you're doing homework and you're like, I'm so smart, I could do this in my head, and then you make a mistake and you have to restart it all over, remember that I said don't do things in your head. 0, 0, -2, 4. Now, I could replace row 1 or row 2 with it. My goal there was to get the 0 in row 2. So I'm leaving row 1 as it was. And I'm replacing row 2. Now I need 2 more zeros, right? Because I need a diagonal of 1s, I need a 0 here, and I need a 0 here. But I didn't need this 0. I like got a bonus 0 there. What could you do? Switch row 2 and row 3. I want 2 zeros in row 3. So I'm going to switch row 2 with row 3. It's not always going to happen. That's a total like bonus that it happened. So 1, -1, -4, 14. 3, negative 2, 1, 15, and 0, 0, negative 2, 4. I switched row 2 and row 3 because I wanted 2 zeros in row 3, but I got them in row 2. With me? Okay. Okay, so now I want one more 0, right? I want a 0 here. I also want these to be 1s. I would never get the 1 before I got the 0 in the row. So getting this 1 before you get this 0 is a waste of time because then you're going to get this 0 and you're going to lose that 1. But if it's easy to get a 1 down here before I go up there, this row is not going to impact that row. So I might as well. If it's a whole number, which most of these are, as soon as you get to a row that has the 2 zeros, see if that's going to give you a whole number. How do I get a 1 here? Multiply by negative 1/2. And that bottom row just got 1, negative 1, negative 4, 14, 3, negative 2, 1, 15, 0, 0, 1, negative 2. I did not have to do that before I could do the zeros, but as soon as I see an opportunity to finish out a row, I took it, especially if it's easy and it's a whole number. Okay, now I still want this 0. Is there anything I can combine with a 0 to make that 3 go away? My only opportunity is to multiply that row with something and then add it, right? So this cannot help me here. I need to cancel that 3 with a negative 3. And I can't multiply 0 by anything to make a negative 3, right? Which means when I go to get that last 0, I have to use row 1 with it. So what do I multiply row 1 by? Negative 3. So negative 3, row 1 plus row 2. Negative 3, positive 12, negative 42. And I'm adding it to row 2. Cancels, 1, 13, negative 27. Yeah. Yeah. That replaced row 2. So row 1, 1, negative 1, negative 4, 14. Row 2, 0, 1, 13, negative 27. Row 3, 0, 0, 1, negative 2. Do I have a diagonal of 1s? Do I have zeros below? So this is in row echelon form. And then comes the back substitution. So x minus y minus 4z equals 14. Y plus 13z equals negative 27. And z equals negative 2. And then I do the back substitution. So z goes in. Y plus 13 times negative 2 equals negative 27. Y minus 26 equals negative 27. Add the 26. Y equals negative 1. That's my second variable. Take them and plug them into the first one. X minus a negative 1 minus 4 times negative 2 equals 14. X plus 1 plus 8 equals 14. X plus 9 equals 14. And x equals 5. So 5, negative 1, negative 2 is the solution. So that process is called Gaussian elimination with back substitution. Tomorrow we're going to do something called Gauss-Jordan, which means get all the other zeros. So fun. Questions? I'm not moving it after that, but. So today and tomorrow's homework is put together. I promise you if you save it to tomorrow, you are going to hate life, friends. I will open it up and tell you where you can get to from here. Obviously, when it says Gosh Jordan, that's where you would want to stop, okay? But I want to tweak it a little bit before we get in there. It is a PDF. You have to show all the work.